All right, welcome to Math 408, L functions and spare packings, lecture 26 or 27, something in that range. So I want to just finish formally what we were doing last time. And I know we talked a little bit about it after class, but just to make sure that the lectures are complete, because not everybody is watching the class in real time, we need to go back and do it. And so the problem that we were looking at was trying to find the vector of minimal length. And it leads to some really good, interesting mathematics that I want to talk about the difficulty in going from a real optimal to a discrete optimal. And so I believe, it was essentially like this. And what was nice is we knew a basis for the lapse. And we were talking about how if you have certain information, some problems are not that difficult. If you have two primes, it's not too bad to multiply them. If you have one prime factor, it's not hard to find the other prime factor if the number is a product of two primes. If things are hidden from you, it's more challenging. And so we have a good basis here. And so I believe we were calling this alpha. We said this was V1, and the length of V1 was 1, and this was V2, and it had length greater than or equal to V1. And I believe we wanted to minimize M1 plus, was it M2 cosine alpha? Or was it sine alpha? So let's see. So we have this vector here. It's going to be V2 minus V1. So this length over here is going to be V2 cosine theta. Then we're subtracting some multiple of V1. So I don't care about the signs of M1 and M2 because I can always change them. So was it M1 plus M2 cosine alpha? Was that what we had? Or did we have sine alpha last time? I thought we had sine alpha. Well, I thought this part over here was going to just be the M2 sine alpha.
Yeah.
So okay. So how would we minimize this? Let's assume M1 and M2 can be real.
Non-zero or?
Yes.
Epsilon and zero or epsilon.
So in the real case, it's not that bad. Is there a minimum in the real if we stay away from 0, 0?
No.
No. Why not? Aren't we supposed to have a minimum?
Be arbitrarily small but not zero.
Yeah. So what breaks down? I mean, aren't we supposed to have a real minimum?
They're linearly independent, so you can't have zero. It is zero.
But don't we have theorems in real analysis that say if you have a continuous function, it attains its max and minima in a compact space. So if we just do this, we're not going to be in the compact space. So let's assume M1 is greater than or equal to 1. And should M1 or should M2 be positive or negative? If we're trying to find a minima. Yeah, so let's just rewrite this. We'll put a negative sign over here. Doesn't really matter. And now we'll have M2 greater than or equal to 0. And so now, do we have a compact set?
Yeah. Well, it's not bounded.
It's not bounded.
It's bound on the bottom.
It's bounded on the bottom, but it's not bounded on the top.
You could just make it arbitrary on the top and just hope.
Yeah, I mean, we know that, if we take, m1 equals
Trillion.
a quadrillion, and m2 equals 0, we're not worried about something like that.
Yeah.
So, yes, it's not bounded, but it's not going to be an issue. And if you wanted to, you could always impose some bounds. All right, so how would we try to find the minima? Now we have a compact space in quotes.
Test
So-
1, 0.
Okay, so you could test 1, 0.
Too low ground. Or an upper ground.
And so if we do 1, 0, that will get us something of length
M1 squared.
m1 squared.
I think we actually might want to expand out the square.
Well, I'm asking more of a general philosophy. So I just want to make sure that we've written things down correctly, because we're not assuming that V1 has length 1. Or are we in this picture now?
Yeah.
We are.
Have it.
I'm sorry?
Don't we have that?
Yes, I think we've adjusted things so that V2, I'm sorry, are we assuming V2 has length 1, or should there be a slight change over here?
There should be a constant.
There should be some constant from the length of V2, right? So we need to fix, so it's actually M1 minus M2, let's call it V cosine alpha squared plus M2 V sine of alpha squared. V is the length of V2, which is at least 1. But so how would we go about trying to find the minima? Partial derivatives, right? So if we call this function maybe f of m1, m2, we could compute df dm1, df dm2, and try to solve them equal to 0. So what will we see when we try to do that? Can you look at this and just see what's going to happen without doing the whole calculation?
Well, it's linear. There's going to be a linear dependence between them, probably.
What do you mean by linear dependence?
Because when you take the derivative, we'll have it. Well, it'll be like df, dm1. Wait, I'm sorry. Like the solution will be like a linear equation.
So let's see what we would get. So we would get, 2 m1 minus m2 v cosine alpha, and then the derivative of this with respect to m1 is just 1. And that should equal 0. Right? And then the next one is going to be 2 m1 minus m2v cosine alpha. And now when we take the derivative of this with respect to m2, we will get negative v cosine alpha. And now plus the piece over here is going to just be plus 2 m2 v sine alpha. And now when we take the derivative of this, we'll just get a v sine alpha. So v squared sine squared. And that should be 0. What?
You get the mv squared cosine.
So we can get rid of the 2's. And then you said we'll have an m2 v squared cosine squared and an m2 v squared sine squared. So it's going to be an m2.
I don't think you want to do that. We know from the above equation
Right.
Because we want to find where these are both.
So M1 has to be M2V cosine alpha.
That same
Well,
chunk is right
Is
below
zero.
it.
Oh, this whole chunk here has to be
Yeah.
0.
That whole
Oh,
chunk
yes.
is 0.
Yes, you're right, that would. And so if that's the case,
Then M2 is 0.
good, so that's even better algebra. So this implies M2 is 0,
Which implies M1 is 0.
which implies M1 is 0, which is not in our region.
So let's change our region.
So the critical point is going to be outside.
We haven't checked the boundary.
Yeah.
So we haven't checked the boundary. And so what's the boundary going to be?
From M2 equals 0 and M1 equals 1. Like,
So we now have to check the boundary. And so what we can do now is if we take M2 equals 0, then it's pretty clear that the minimum is going to be 1. And so can we do any better? Well, the nice thing is we can just take the special case when M1 equals 1. And so we would then get 1 minus M2V cosine alpha squared plus M2V sine alpha squared. I'm sorry?
you don't get better. I think. Actually, no, you.
No, and this is the question: is can you look at this and can you see what's going on? We're subtracting our here. Maybe if cosine alpha is kind of large, we're going to subtract off a good chunk here before we square it, and that might be better than squaring that part over there.
I think we should square it out.
Yeah, and you're going to get.
So now you at least have a function of just one variable. So we have g of m2 is 1 minus 2 m2 v cosine alpha, and then we'll have a plus m2 squared v squared, so it'll just be a plus m2 squared,
Isn't there a v? Isn't there a v?
m squared v squared, right? All right, how do we handle this? Derivative. So g prime of m2 is going to just be minus 2v cosine alpha plus 2 m2 v squared. And so we want that to be 0. So that should give us m2, the 2's cancel, one of the v's cancels, and we'll get m2 is going to be cosine alpha over v. And then we can just put that in and see, does it do anything better? Well, what's nice is if we do that, we would get 1 minus
2 cosine alpha squared.
so I might just plug it in directly over here.
Yeah.
So 1 minus 2 cosine squared alpha. And then the next one, the v squared cancels, and we'll get plus cosine squared alpha. And so then that would just be 1 minus cosine squared alpha. And alpha is fixed. So we're not in a situation where alpha can get smaller and smaller and smaller. Is there anything else we need to do?
Check.
We have to check the endpoints as well. Okay, so this is how you would handle a calculation like this. This is going back to our multivariable calculus days. We don't have a nice constraint. We often had Lagrange multipliers when you had your function f and g. You took the gradients, so the gradients had to align. We're not in that situation. There is one thing that you can do sometimes in problems like this, that often gives a decent answer even if it's not the best. And I think it's worth seeing how to get decent answers that aren't the best. Good approach. Let's look at the two terms again. So we have m1 minus m2 cosine alpha squared plus m2 sine of alpha squared. And this is similar to one problem that was done in the problem solving class years ago. Do you know which problem I'm thinking of? We have two terms. What we could try to do is say, let's equate them. Because maybe as we make this term smaller, that's probably making this term larger and vice versa. That often happens. It may not happen in this particular problem, but as a rule of thumb, as a nice approach to attacking problems, if you have two things with competing influence, one of the things to do is to be democratic and say, let's make them both equally bad. And so if we do that, we would say, let's let m1 minus m2 cosine alpha equal m2 sine of alpha. And then you would get m1 is equal to m2 cosine alpha plus sine of alpha. How would we finish this?
M1 with a lower bound of 1.
Good, we know m1 has to be at least 1, so we would take m1 equals 1. And so we would get m2 is 1 over cosine alpha plus sine of alpha. And there is a typo here. Yeah, oh, you omitted the v. So there's got to be a v over here, a v over here, v, v. Should be a v over here. And then we get a 1 over v coming over here. So it's interesting to compare this to what we had before. They both have a 1 over v. The other one had a cosine alpha upstairs. This has a cosine alpha plus sine alpha downstairs. Not bad. We at least sniffed out that it should be some constant times 1 over v. That we could take m1 to be 1. And so this gives you some idea of, if you wanted to try a problem like this, maybe you guess m1 equals 1, m2 is some constant divided by v. And it gives you some idea of what the scale is to attack a problem. So I want to, the problem that this was somewhat similar to was the egg drop problem, where we had 2 eggs and you wanted to minimize how many drops you needed to figure it out, and you had 2 different competing influences. The more floors you dropped initially, the better if it doesn't break. So what I want to do now is I want to talk about one particular problem where it is easy to go from the discrete optimal to the real optimal. Question or?
Why not?
Okay. I'm sorry? Sorry, the other way around. To go from the real optimal to the discrete optimal. Normally you cannot pass from a real optimal to a discrete optimal. But there is one setting where you can. I don't remember if I did this problem in operations research. I'm pretty sure I did it in problem solving. It is one of my favorite problems. It's essentially almost everything you need to know from differential calculus. So here's the problem. You have some number n, and you want to write it as a1 plus a little n. Each ai is an integer, and you want to maximize the product. So I have a fixed sum of positive integers. I want to maximize the product. If I didn't assume that the a's had to be positive, how large could you make the product? Yeah, as big as you want. Yeah, you could do negative n plus n plus n. Nope, that won't work. But I could do negative n minus n plus 3n, say, for instance. And then that will sum to n. And by having it as 3 terms like this, I can make the product as large as I want. So the problem isn't interesting unless I assume the a's have to be at least 1. So if you have seen this problem and remember it, you have to be quiet. Have you not seen this problem? Good. This is one of my absolute favorite problems. Yes?
Is n fixed?
Little n is free.
Oh, little n is free. Okay.
So n is free. Can you tell me anything about the AIs? Other than they will rule the world and we will be their loyal servants.
You probably want them to be more than 1.
Right.
Them to be greater than 1.
Right, does it help to have any of the AIs equal to 1?
No.
So we know 2 must equal to AI. What about on an upper bound? Would you ever want an AI to be 10?
As long as n is.
Well, no, if one of these terms, would you want one of these terms to be 10?
No.
No, what could you do?
2, 2, 2, 2, 2, 2.
Or better yet,
5,
8 and 2. Would you want any of them to be 9? No, what would you?
3.
I'm sorry?
Like 6 and 3.
I don't want to do 6 and 3.
7 and 2.
I want to do 7 and 2.
7 and 3.
What do you think I want to do for 8?
6 and
6 and 2.
2.
So 5 is 3 plus 2. What about 4?
Some would say it's 2 plus 2.
Some would say 4 is 2 plus 2. And the
Well,
freedom,
that's equivalent.
it's equivalent. So do you want to say if you ever have a 4, replace it with 2's? It's equivalent. Is it worth making that as a rule?
Yes.
Yes, why?
And you can make the just nice.
It's very much tied to it's nicer.
The math is going to be
If you
convenient.
have an odd out, then you can add then you have 5.
Well,
If not 3,
would you rather have the AIs to range between 2 and 4 or between 2 and 3?
2 and 3.
Yeah, it tightens them a bit. And so even though I'm indifferent, let's replace the 4 with 2 plus 2. Once we get to 3, we can't do anything. So we know every AI is at least 2 and at most 3. All right, that's not that much freedom. Which do you think is better, 2's or 3's?
3s.
Okay, why 3's?
3 times 3 is better than 2 times 2.
3 plus 3 is 2 plus 2 plus 2, last time I checked. And that takes a product of 9. That takes a product of 8. And so we basically want to have as many 3's as we can, and then just 2's at the end. Ah, so wait, email me for extra credit. What did you just say?
Plus your e.
So here is the number line. Here is 2, here is 3, here is approximately e, and here is 2.5. What is going on is exactly what you said, is e is closer to 3 than 2. And this has applications in computer science. Yes, that for disk storage, base 3 is better. And there's a wonderful article about base 3 over base 2. For the most part, base 2 is the glory base. Everybody loves base 2. The other bases don't really get the time of day. But for some things, base 3 is better.
So like the, I forgot what it's called. Can we cut it from middle straight out?
Oh, the Cantor set?
Like, so it's not.
Yes. So the Cantor set is equivalent to all numbers that have no 1's in their base 3 expansion. And then you can convert that to a base 2 expansion by changing all the 2's to 1's, and then the 3 to the n to a 2 to the n in the expansion. And so the Cantor set is actually equivalent in a cardinality sense to the real line. But in another sense, it has a different length. It has a different dimension. So there's some really interesting stuff going on.
For this, if we did it
continuously?
Well, let's do it continuously.
E will be the same.
So all I need to change now is, do we still want the a's to be at least 1?
Sure.
Yeah. So let's just get rid of the word integer. So we know we can't now say that it has to be at least 2. Does the argument from before work that it's still at most 4?
Yes.
Yeah. So we know the a's and little n has to be an integer. How should we attack this problem? So we don't know what little n is.
Would you want AI to be constant?
Okay, why do you want
N is still an integer, right?
n is still an integer?
That's hard.
So I agree with you that we want the a's to be constant.
You did say for the last thing that a good approach is to set things equal to each other.
Yes. And so you might guess that all the a's are constant, but how many of the a's should we have? That's the problem, is what constant?
N over E floor.
Okay, so you're on fire today.
Awesome.
Have you seen this before?
No.
Okay, you're on fire today. So, but how do we figure out that they should all be the same?
Seems like a good approach.
It's a good approach.
Because if they're not, make a and G,
So we have the A and G inequality. So the other thing is, let's look at the case of just n equals 2. This is the Farmer-Brown problem. You know, Farmer-Brown, have any of you ever read Click, Clack, Moo? Cows that type?
Yeah.
Farmer-Brown has a problem all day long. His cows like to type click, clack, moo, click, clack, moo, click, clack, moo. So he only will consider rectangular pens. And so if you have a rectangular pen, let's say it's A1 by A2, it has a fixed semi-perimeter. A1 plus A2 is the semi-perimeter, which is n, and we want to maximize A1 times A2, which is the same as maximizing A1 and minus A1. You don't even need calculus for this. 0 and it's a parabola like this, it's at the middle. And so we know that whenever we have a situation like this, if A1 and A2 are not equal, we replace with A1 plus A2 over 2, A1 plus A2 over 2, and that will do better. Have we done this problem in this class yet or no? I don't think so.
Farmer-Brown problem.
I'm sorry?
This
one.
rectangle one?
Yes. Okay, I just like the following. There's another version of this where he has a wall. Did we do this?
Yeah, now we did.
Yeah, and we had Aquaman below.
I remember this because there's the flip.
Right,
Oh yeah, you said you did it with your son or something.
right. Because you can imagine Aquaman is making a pen for his fish. Right. And so we know that if we have just 2, we want to have them be the same. Okay. How does that help us?
You can fix n minus 2 of them, so the other 2 moving.
Good. So if we have 2 of them that aren't the same, we can make it larger by making them the same. But we still don't know what to take for little n. So I agree with you that if we know n, so if we fix n, best if all the same, so ai would be n over little n. Do we know that if we fix little n, a maximum exists? Yeah, it's a compact set. So for each little n, we know what's best. Now what do we do?
Just find the best among those.
Okay, so let's introduce a function. F of n is going to be n over little n raised to the nth power. How do we maximize this? We can't take a derivative of this. This is only defined on integers. Make it continuous. Continuify it. So let's let f of x be n divided by x to the x, which is e to the x log of n over x. And now we have a function of a real variable. Now we can use calculus. All right, so we want to calculate what goes on at the endpoints. The endpoints are easy. Right? If you take everything to be 1, the product is 1. And then, x is clearly not going to be larger than n. And if x is equal to 1, you have a product of n. You can do better by taking n over 2. So I'm not worried about the endpoints. So let's take the derivative. So f prime of x, when we take the derivative, we just get our function back again. And then we have the derivative of the top piece. So it's going to be the log of n over x from this plus x, and now we have to take the derivative of the log of n over x. That's the log of n minus the log of x. So its derivative is negative 1 over x. Okay, and we want this to be 0. So this implies the log of n over x equals 1. So n over x equals e. So x is equal to n divided by e. So we have the real optimal. And now, what I want to do is I want to go to curve sketching. This is something that we were taught when I was learning calculus decades ago. I'm curious if this is still taught, where you write down here the first derivative and the second derivative, and you use the signs of these functions to figure out, is it increasing, decreasing concavity?
I did something like that.
Something like this? Vaguely.
Yeah, we did this in the past.
Did you do this in the past?
Yeah.
Okay. Did any of you ever learn how to use log tables or trig tables in school? Okay, so I was taught how to do that. I was not taught how to use a slide rule. I had to figure that out myself.
Wait, so
Is a log table? Is a table?
A table of logarithms.
Okay, I see.
Yes.
you have to do it log 1, log 2, log n?
And interpolate. So what are the key points? We have 1, we have n, and not to scale, we have n over e. We know if x is less than n over e, so n over e, the first derivative is equal to 0. If x is less than n over e, then this number here is going to be the log of something greater than e, so it's going to be positive. When x is greater than n over e, this is the log of something less than e. Its logarithm, when we subtract 1, we're going to get something that's negative. So we know the curve has to look something like this. Without knowing the detail, it has to be going up to a maximum and then going down. Where is the integer maxima? Or at least where are my candidates? Yeah. The 2 points, to the right and the left of n over e. So you look at the floor and the ceiling of n over e. So the floor. I'm sorry? So actually, this might be an interesting question. I'll send this as homework. Which wins for n less than equal to 10,000. How do I expect you to do this? Computer,
Yeah.
right? If you guys all want to do it together and code together, I mean, you should know how to write a simple code like this and just investigate. What questions might you ask?
For which values?
Well, so, I mean, one is, which values? But let's take a step back. What might you be interested in knowing?
Which one is it closer to?
What do you mean by is it closer to?
Is N over E, like, is it more than 0.5 or less?
Good. So what fraction of the time is it each? What would be your guess?
Small. E's 2.7.
But again, what matters is when we plug it back into the original function, I have no intuition right now on this because we have to feed it into this.
Yeah, it depends on the behavior of like the function.
It depends on the behavior of the function. So a simple question is, as we keep increasing n, do you expect to be half the time in each one of these? And then, after that, which do you think is going to be larger? So just see what you can say about a problem like this.
I don't, wait.
Oh, actually, I think asymptotically it should be 50-50.
For which? For this or for putting into the function?
For the bottom one.
For this one, these two should be taking half the time.
I think asymptotically, because the derivative is continuous, so like as you get closer, I think it should.
So wait, are you saying that just you should be you're saying that half the time it should be the floor that maximizes this, and half the time it should be the
I
ceiling?
think asymptotically, yes.
Okay.
I don't know, like, yeah.
It's the most natural thing to conjecture. And I've never mentioned that question when I've taught this class before, when I've taught this lecture before. It's something I probably should have talked about. It's trying to create new problems from things that you're doing. And one of the most natural questions we have is when you have options, how often does each option happen?
Yeah, when we say wins
So wins is the one which maximizes this.
for all n?
No, for fixed n. So as you vary n, sometimes this is going to be the one that will be the integer max. Sometimes this will be the integer max.
So it's to say which one occurs more often?
Yes. And then you might have stretches where one of them is winning. And then you might have a long streak of one, and then the other one wins for a while, and then the other one. So it might become really interesting to come up with what is the right metric to count. And so this leads naturally to a lot of different notions of how should we count things. And so
Do you think we should count by discrete?
well, I'm going to show you a nice way to count. And I was not actually planning on doing this today, but I'm finding this interesting. So, counting. For the most part, you have been trained to count equally. Right? If you have a bunch of points, all points are assigned the same weight. One of the problems with that is if you have infinite sets, it becomes a little bit challenging. So there is analytic density. Sometimes called Dirichlet. And what you do is you have some subset A of the natural numbers. And so today I'm going to have my natural numbers start at 1. And what you'll do is you'll say the analytic density of A is going to be, I'll put like an S up there, is going to be the sum n less than or equal to big N, n is an A, of 1 over n to the s, divided by the sum n less than or equal to n, 1 over n to the s, and take the limit as n goes to infinity. when will I know if this limit exists?
Does it always exist?
Well, it could do, I mean, depending on how pathological the set A is. I might be able to come up with some kind of strange thing where maybe it doesn't exist. Can anybody give me conditions on S where I should be happy?
S greater than 1.
Yes. You know, either S greater than 1 or a real part of S greater than 1. In those cases, now you have a series that converges absolutely. And then no matter what set A you have, it will be fine. So if the real part of S is greater than 1, everything is fine. And you could look at the limit as S goes down to 1. Sometimes people write this as S goes to 1 from above. Both notations are used. And do the analytic density of A would just be the limit as S goes to 1 from above, so I'll mix them. The sum n in A, 1 over n to the S, divided by zeta of S, the Riemann zeta function. So here, zeta of S is just the sum 1 over n to the S, and it goes from 1 to infinity. And so for each value of S greater than 1, this actually exists and makes sense. What kind of properties do you want the analytic density to have? So is the analytic density a notion you've seen before for density?
The regular density?
Yeah, okay. So you've seen the regular density. So what should the density of the evens be?
1/2.
1/2. What should the density of the numbers that are congruent to 1 mod 17 be? 117. So what would you like to be true? Okay, so if they're always the same, is there any reason to introduce the analytic density?
Well, the analytic density can extend.
Okay, so give me the exact statement you want to be true. Theorem.
Where regular density exists.
Good.
analytic density is the same.
If regular density exists, then d analytic density of A equals d regular of A. So the analytic density should not give you something new. I will risk a cultural question. What movie has the line, "I am your density"?
Hint. Is it,
The last line of the movie is, "Roads, where we're going, we don't need roads."
Back to the Future?
Back to the Future.
What
What was
did
his,
he
what,
say? I am your density.
George McFly, he meant to say, "I am your destiny," but he was a little tongue-tied and said,
When
"I
he-
am your,"
When he was asking her.
when he was asking her out. Yes, "I am your density." So what I like about this is you came up with a natural theorem on your own. So now, how would we define natural density? I love that we have a theorem without even specifying what one of the quantities is.
It's just the same as above, but instead of whatever entity it has, just put 1.
Okay. So d regular of A would be the limit as n goes to infinity of the sum.
Probably just do it as cardinalities.
Yeah, so let's do,
I like,
Yeah.
let's do like this. It's the number of n less than or equal to n such that A sub n is an A divided by n. So homework, oops, give me 1 second. Hello? Yes? Yes. Can I call you back in about 2 minutes? Okay. Okay. So let me just quickly finish this up. So for homework, prove this.
The theorem or the density?
Prove this theorem. So we will add that to the homework problem.